Thank you very much, Rita, for the introduction, and thank you to the organizers for inviting me. This is the second time that I managed to sneak in a GR conference, not being a GR person at all, but I enjoyed very much my last time in Crete, where I met half of the people, so I'm happy to be here. And I have to apologize because this is again going to be a stability result about a flat metric. So no black holes, but okay. This is what I was able to do. But hopefully I'll try to make it enjoyable and, just before lunch. Okay, so this is a joint work that we did a couple years ago in collaboration with Cécile Hunot, who is a DNS at CNRS in France, and Zoe Wyatt, who's at University of Cambridge, and is about the global stability of this Kaluza-Klein spacetime. So what is the general setting? Okay, so first and foremost, the plan of the talk will be of giving an introduction of, as I was saying, the setting of this problem. And in the second part of the talk, I will discuss more precisely the PDE problem that we looked at. And towards the end, I will give some hints of the proofs. Okay, so the general setting for the problem that we got interested in is theories of higher dimensional gravity. So these theories like supergravity or string theory received a lot of attention from the theoretical physics community in the last century as, on the one hand, possible models for quantum gravity, but also as being good candidates to give a unified descriptions of the main forces in nature. So gravity, electromagnetism, weak force, and strong force. And so in order to try to build a theory that can encode all of these forces, you have to suppose that the universe we live in is higher dimensional. And more precisely, it has dimension 4 plus d, where the d additional dimensions are compact. And why do you have to assume this compactness? Well, because if you want to build this higher dimensional theory, at least the very first thing that you should be try to do is to recover the well-known four-dimensional physics from the higher dimensional models. And this is why the additional dimensions are supposed to be compact in order to do such a reduction. And also, if one really believes that these higher dimensional theories are important, you should not only deduce the four-dimensional physics, but study all the predictions that these models can give. So for example, in string theory, the universe is supposed to be 10-dimensional and the space-time to be a product manifold of the form r to the 1 plus 3 times x, where x is a Calabi-Yau threefold. So this is what is called Calabi-Yau compactification. And the mother of all these higher dimensional theories is the Kaluza-Klein theory, which was formulated already a century ago by physicists Kaluza and Klein in 24 by Kaluza, and then it was revisited by Klein 2 years later. And this theory is just 5-dimensional. It was introduced to give a unified description of gravity and electromagnetism. And the additional dimension that is introduced is compactified over a circle of a very small radius. You have to imagine the radius of the order of the Planck constant, so that at low energies, one can recover from the 5-dimensional Einstein equations the 4-dimensional Einstein-Maxwell scalar field equations. So I will return maybe in a slide or two towards this reduction and the deduction of the description of gravity and electromagnetism from the 5-dimensional formulation. And the ground state of the 5-dimensional theory is the Kaluza-Klein spacetime, which is essentially your favorite Minkowski solution, but in this 5-dimensional setting. So the spacetime is given by this manifold M, which is diffeomorphic to R to the 1 plus 3 times the circle, equipped with the flat metric G bar, where T and X are here the variables in R1 plus 3, and Y here and throughout the talk will be the variable living on the circle. Okay. So how does one recover gravitation and electromagnetism for this, starting from this 5-dimensional model? Well, this is what is called the zero mode truncation. This is done by using the zero mode truncation and the Kaluza-Klein reduction, which I'll explain on a simpler model of a wave phi traveling on this Kaluza-Klein background. Okay. So here phi is just my wave here. And if you do a frequency decomposition of your phi along the, along in the y variable, so you write essentially your Fourier expansion here, you see that each k mode of the solution of the wave phi will be solution to these Klein-Gordon equations, right? So the zero mode will be a linear wave, and all other non-zero modes, phi k, will be massive waves, and with mass given by mod k divided by r. Okay, and then now physicists say that since you assume that the radius r is very, very small, these massive waves have a mass that is too big to be physically relevant. And so these modes are usually neglected. In other words, one only assumes that a wave phi traveling on this background does not see the y variable. And so now if you consider, if you consider a 5-dimensional metric, G5 here, solutions to the Einstein vacuum equation, so Ricci flat, that does not depend on the compact direction. One good way of writing it, one good ansatz is to write it under the following form. So essentially, this 5-dimensional metric, you can look at the coefficients according to the direction. So you have a fifth direction, and then all the other ones. And so you see that, so here you have, okay, this G44, which is a scalar function. This G mu 4 correspond to a 1 form. And here, these other ones with mu and nu ranging from 0 to 3 is a 2-dimensional, is a 0-2 tensor. And written under this form, you do your computation, and you see that the G here, the 1 form A, and the scalar function phi solve the Einstein-Maxwell scalar field system in 4 in 4 space-time dimensions, which is written here, right? So you have here the Einstein equations with the scalar field on the right-hand side, and the part coming from electromagnetism, Maxwell's equations, and the equation for the scalar field. And you see that you cannot really get rid of the scalar field because this is coupled to the Maxwell field. So, okay, one cannot really get Einstein-Maxwell, but Einstein-Maxwell scalar field equations. Here, so it's this is maybe an issue with my, it should be something related to maybe alpha or beta here. It should be a typo. It's a typo. Yeah, I think so. My apologies. All right. And so this was about the reduction to the 4-dimension physics. And then, as I was saying, it's also important to study the predictions of the higher dimensional model. And our goal here was to, in fact, do something in that direction and to prove that the Kaluza-Klein spacetime is classically globally stable for the higher dimensional Einstein vacuum equations, okay? And globally stable under, of course, suitably small perturbations that in this work also depend on the compact direction. And since this work does not really depend on the size of the circle, for convenience, we just fix R to be 1. Okay, so thanks to the fact that Sanjin gave a talk at the beginning of this morning, I can essentially say very few words about this slide. Of course, the Einstein equations can be have a well-posed initial value problem formulation, and the local well-posedness theory was set in the works of Choquet-Bruat and Choquet-Bruat with Garrosh. The only thing that I will say here is that their proof is done in the 4-dimensional setting, but in reality, it applies very well to higher dimensional setting. And even in the case where the manifold is a product manifold and not just R to the 1 plus 3 case. Okay, so it gives a local well-posedness theory for our setting of the Kaluza-Klein theory. There is also a work by Dai, almost already 20 years ago, for the positive mass theorem for spaces, okay, with supersymmetric compactification, and this one falls into it. And yeah, I will also cite this work by Cécile Huneau and Caterina Valcu, in which they do construct solutions to the constraint equations for this problem. So they construct solutions to the constraint equations on product manifolds R to the n times TD, okay? So this is to say that, okay, local well-posedness for this problem is set, and we look at the global well-posedness type of problem. And this is the result that we got. So consider an initial data set, sigma G0 and K0, to be any set of any smooth asymptotically flat data where the initial manifold is a 4-dimensional manifold diffeomorphic to R3 times S1. Equipped with a Riemannian metric G0 and where K0 is a symmetric to tensor. And we suppose that our starting metric G0 is essentially a perturbation of the initial datum for the Kaluza-Klein metric, okay? So it accounts here, so the one here is for the extra dimension, and this term here it accounts for the ADM mass, as Sanjin explained in his talk. And we suppose here that our perturbation decays in R with this rate, R to the -1 minus kappa, and K0 as R to the -2 minus kappa with kappa positive. And kappa not being the kappa of the previous slide, of course. Okay, and we suppose that these quantities are also suitably small. So under the assumption that the data satisfy the constraint equations, we can construct a unique causally geodesically complete space-time solution to the Einstein vacuum equations, which asymptotically converge to the Kaluza-Klein space-time G bar, metric G bar. Okay, so also, I mean, already this morning we've seen the state of the art. about the stability of the Minkowski metric. Of course, so here I added this brand new result on the stability of Minkowski, and also put like a question mark to put pressure on you to publish this soon. Okay, we'll also mention that, of course, there are these results for the stability of Minkowski for the Einstein vacuum equation, but there is a very vast literature about the stability of Minkowski for other, for the Einstein equation coupled with other matter models. And in this setting, I will just, so for the purpose of this talk, I will just mention these works for Einstein-Klein-Gordon type systems, where global stability was proved in a work by Le Floch and Ma, in which they assume essentially that their initial data coincide with Schwarzschild outside some ball. And then the work by UNESCO and Posader that you also mentioned, Sanjin, where okay, data have the data have some decay at infinity, so a more general class of data. So then what do we know about the stability of the Kaluza-Klein metric? So I will mention for this the seminal work of Witten in 1982, where he talks about the semi-classical instability of the Kaluza-Klein metric, in a sense that I am not 100%, that I don't understand at 100%, but probably what I can tell is that the semi-classical instability is understood as the failure of the positive mass theorem for Kaluza-Klein, starting from data that have the geometry of the Kaluza-Klein metric, but different topology. And the topology is not that of R3 times S1, but rather R2 times S2. And in this case, if you start with spacetimes that have this type of topology, you can construct a development that goes asymptotically to the Kaluza-Klein metric, but has positive energy. No, sorry, zero energy, so zero energy in the sense of the ADM mass. All right, but in the same paper, he also gives heuristics for global stability. And the question of global stability was already tackled by Wyatt in her PhD thesis, where she proves that, in fact, this Kaluza-Klein metric is globally stable under toroidal independent perturbations, meaning perturbations that do not depend on the compact direction. And there is also an analog of this result for cosmological Kaluza-Klein spacetimes, done by Branding, Feynman, and Kronke. And let me also mention that there is a work by Anderson, Blue, Wyatt, and Yao from 2020, where they study the global stability of spacetimes with supersymmetric compactification. So these spacetimes have the following form. The manifold is a product manifold as such, so R to the 1 plus n times k, where K is a compact Ricci flat manifold that has spin structure and non-zero parallel spinor. Think of your Calabi-Yau favorite type of manifold. And n here is taken greater or equal than 9, so that essentially the linear decay survives for the is strong enough that can allow you to handle the nonlinear terms, but this type of stability is conjectured to hold true even for n down to 3. Okay, so our result is a global Well-Posner result for Kaluza-Klein spacetimes under general small perturbations, meaning, when I say general, I mean also depending on the additional coordinate. And it applies also to higher dimensional settings, r to the 1 plus n times the d-dimensional torus for n greater or equal than 3 and d greater or equal than 1. And it also provides a new proof of the global stability for the Einstein scalar field system and Einstein-Maxwell scalar field systems. All right. So, okay, and since I told you at the beginning that I wasn't a GR person, now I will move to dispersive equations, which I know a little bit better, and I will place myself, I will turn this geometric problem into a system of PDEs by rewriting the problem using wave coordinates. So I will take my favorite wave coordinates here, express the metrics in such coordinates so that the metric satisfies the so-called wave coordinate condition written here. And then I introduce little h, the perturbation tensor, so the difference between my unknown metric G and the Kaluza-Klein metric G bar. And capital H here will be the difference between the two inverses, which is essentially the inverse of little h up to quadratic corrections. And so if G solves the Einstein vacuum equations, then my perturbation tensor will be solutions to this system, coupling to this system, which is a system of wave equations on my product space with initial data that are compatible with the constraint equations. So this is a wave equation, as you can see from the linear operator over here, that is quasi-linear. It has, in fact, quasi-linear interactions given by this term. And in the right-hand side, I put everything that is semi-linear. This right-hand side contains both quadratic and cubic terms. So for the rest of the talk, I will forget about the cubic terms, which are just short-range perturbation for the equation, and focus on the quadratic terms. And among the quadratic terms, there are two. The quadratic terms will be of two kinds. So there will be null terms, meaning linear combination of these two quadratic forms here, and terms that are called weak null that have instead this type of structure. Okay. So the main theorem is the following: assume that you have a kappa positive and fixed, which will correspond as I said a few slides ago, to the decay that we're asking for the data at infinity. And so we prove that if the data are sufficiently regular, so of the Sobolev regular of this type, Hn with n greater than 14, and epsilon is sufficiently small, then so if the data are small, decaying at infinity, so essentially I'm saying that the H1 norm of my data decays as r to the minus 1/2 minus, and I get further decay when I add derivatives. And if I have this extra smallness condition here, then I can construct a unique solution to my problem with this data. And the solution decomposes into two parts. One that takes into account the mass term, and the other one, H1, that is small and will decay as 1 plus t plus r to the power -1 plus some gamma, and gamma is arbitrarily small, but fixed. Okay, so, and the proof of this result is somehow classical, right? It's based on a bootstrap argument where you want to propagate higher order energy assumptions and pointwise bounds on the solutions. And the proof, it is articulated in 2 steps. In the first step, you want to write down quasi-linear higher order energy inequalities for your solution and sharp pointwise estimates. And once you have those, at the second step, you want to estimate the trilinear and quartic terms that come in the right-hand side of the energy inequalities from the nonlinearity. So, and the key tool for that is the vector field method of Kleinerman, in which you exploit the symmetries of the system and make use of the vector fields that come with them. So the admissible vector fields for these problems are the following. So the usual derivatives along the coordinate axis, reminiscent of the fact that the problem is invariant by translations. Then the Euclidean, these omega ij's, so rotations in the x variables, and the omega 0 I vector fields, the boosts, reminiscent of the fact that there are invariants by hyperbolic rotations of the system. And observe here that we were, I said that my problem is written as a system of wave equations, but these are wave equations on a product space where there is a compact dimension. And in reality, they correspond to, because of that, and unlike wave equations on R to the 1 plus 3, the system is not invariant is not scaling invariant. So the scaling vector field is not an admissible vector field to be considered. And in fact, this is due to the fact that our system is actually equivalent to a system coupling wave equations to Klein-Gordon equations, to actually an infinite tower of Klein-Gordon equations. Recall, in fact, that you can Fourier decompose your metric coefficients along the y coordinate and see that the 0 mode of the solution corresponds to a massless wave, but all other non-zero mode is a massive field with mass given by mod k. And so, as I said, this turns our problem into a system, a 4-dimensional system coupling wave equations to an infinite tower of Klein-Gordon equations with increasing masses. And let me point out to another thing, which is that the massive field appears in the curved background, which is a feature that is different compared to Einstein-Klein-Gordon systems, right? Okay. Where the massive field only appears as a semi-linear term, so it doesn't appear in the curved background. Okay. And so what is the issue related to this lack of symmetries? Well, first of all, usually when you want to obtain pointwise estates from your energy bounds, and you usually do that using Kleinerman-Sobolev inequalities, which are a way, you have to think of them as Sobolev injections somehow, that allow you to gain from the L2 bounds here some space-time decay. And you're able to do that by, if you have a control in L2 of the solution, of the derivative of the solution, with some vector fields. But in these vector fields that you put on the right-hand side, you only have to consider the scaling vector field. So for this problem, you cannot do them. You cannot do that because you do not have a good control of the L2 norm of the solution on which, if you let the scaling act on it. Then another thing you would like to do but cannot exactly do is to say, okay, but you can circumvent this problem by considering hyperboloids. Because if you consider hyperboloids and you do an analog of these Klenerman-Sobolev inequalities, you only, so you can get again t to the 3 pointwise bound in t to the minus 3 half for your solution if you know how to control the L2 norm of the solution, where here the Z vector fields do not make appear the scaling anymore. These are just a vector field tangent to the hyperboloid. Of course, you can do that, but you can do that just in the interior of the light cone, because in the exterior, these hyperboloids are time-like and you don't have a good control on them. And so, the issue in our problem is that we are not just considering initial data that are compactly supported so that we can restrict to the analysis to the forward light cone. We also have to take into account what happens for the solution outside the light cone. And so in order to tackle this problem, we decide to essentially run the analysis separately in the exterior and the interior of an hyperboloid, an initial hyperboloid, which asymptotically tends to the flat cone, and the analysis done in this way becomes okay. This is possible to do that because essentially the analysis in the exterior doesn't depend at all from the analysis in the interior, right? So we can carry on the analysis in the exterior, get our global existence result, and then take care of the interior. And this is what I'm going to explain in the following slides. Okay, so what we do in the exterior region is that we foliate the space-time just by constant time slices and propagate bounds on weighted higher order energies of the solution. So these are the weighted energy functionals that we consider. Okay, so kappa here will again be related to the decay that the data and then the solutions is required to have. And observe that this energy functional, so it controls the H1, the weighted H1 norm of the solution, but it also controls this space-time integral of the tangential derivatives of the solution to the outgoing cones, as well as tangential to the circle. So these are, derivatives that behave because of that will behave much better than usual derivatives. And we propagate these types of bounds. So we can only propagate energy bounds that are allowed to grow at a small rate in time. All right. So we have two of them because essentially we're saying with this with the second one that higher order derivatives with usual derivatives, they should gain decay in space. And then we will use, once we have our energy bounds, we can essentially use weighted Sobolev and weighted RD inequalities to get pointwise decay for the solution. In particular, get for the usual derivatives of H, the decay that is expected, so 1 plus T plus R to the minus 1 plus sigma, and the decay with respect to the light cone R minus T to the minus 1/2 minus kappa, and extra decay for the tangential derivatives, meaning that we have 1 plus T plus R to the minus 3/2 plus sigma, and then R minus T to the minus kappa. So the analysis in the exterior due to this weight in the energies pretty fairly straightforward. So once we have this global existence result in the exterior, we can move to the analysis in the interior. And now that we are in the interior essentially in the interior of the light cone, we can foliate the space-time by hyperboloids and introduce energy functionals on hyperboloids that are given as such. So essentially, this energy functional controls the tangential derivatives here to the hyperboloid, the tangential derivative to the circle, and this S over T dt derivative of the metric H. Okay. And then the point here is that you cannot just carry the analysis and just for your whole solution H, because you will never be able to close your estimates. And really at this point, you have to remember that your solution is not just made of waves, massless waves. It contains two parts, massless waves and massive waves. So you really have to take advantage of this feature at this stage of the proof. And so you have to distinguish between zero modes and non-zero modes. And actually, you don't really have to deal with each non-zero mode. You can just group them together and run the analysis for them. So it's only enough to introduce the zero mode of the solution. So you average on the circle. And so these are my H, what is this? H flat, I guess it's called in English. And H sharp here will collect all the non-zero modes of the solution. And one important feature of the fact that the compactification was on the circle is that now when you look at the product of two functions, f times g, and you take the zero mode, this zero mode is simply the product of the zero modes of the two factors plus the zero mode of the products of the two non-zero modes. And this feature is really relevant for this problem. Essentially, it's telling you that it's saying that if you take the wave part, the massless wave part of a product, this is the product of two massless waves or the product of two massive waves. You don't have mixed products, massless times massive. Okay, and so once we have this, we propagate. The goal is to propagate a hierarchy of energy bounds, higher order energy bounds, and sharp pointwise estimates that I will try to explain a little bit. So when you consider higher order derivatives for your metric perturbation H, you can only, so what we propagate are these bounds on hyperboloids. So we propagate a bound that grows in S with a power 1/2 plus this zeta. We have to allow for a bigger growth, which I will explain. So I will explain why this bigger growth comes out. However, for the energies of the massless part, we only propagate a small growth in time as to the zeta. And then whenever we consider energies, but with a lower number of vector fields acting on the solution for the full metric components, we can also propagate a small growth in S, but this time S to the delta. And then we also propagate pointwise bounds. In particular, for the massless part, we propagate a bound, a decay t to the -1. For the massive part, we propagate a bound t to the -3/2 with some loss S to the gamma. And now it's really important to have a hierarchy between these parameters, zeta here, delta here and gamma. And in particular, we have to ask for zeta to be much smaller than gamma, to be much smaller than delta, to be able to close the estimates, to close the argument. And so, all right. So how do we propagate the energy bounds? Okay, we have to estimate the nonlinear terms. So I said that among the quadratic terms, there are the null terms, and these are the easiest to estimate, because essentially the main property of null terms is that they are essentially made of, they always make appear tangential derivatives, and tangential derivatives do behave better, so we gain. These can be estimated by an integrable power of t. Then we have the weak null terms, which are these ones, and it was shown in the paper by Lindblad and Roniansky that, okay, these terms do not satisfy, do not have a null structure, but they do have some structure when you look at them in the null frame, right? So you introduce your null frame where with vectors L being dt plus dr, L bar being dt minus dr, and S1 and S2 being angular derivatives. And their main observation was that when you rewrite these weak null terms with respect to the null frame, you realize that you don't have all types of products, but you only see either products of metric components that have been contracted with at least one tangential field, or if both indices have been contracted with L bar, which is the bad direction, then this metric coefficient is multiplied by a very good one, which is the one where you have contracted with L and with L twice. Okay, and so why is this good? Because so whenever you look at metric coefficients where you have contracted with a tangential derivatives, okay, so I started with the last line. Whenever you look at coefficients where you have contracted with tangential derivatives, you realize that these metric coefficients are solutions to wave equations in which in the right-hand side, there are only quadratic terms satisfying null, that have a null structure. So you can get better decay for these ones. These are these have t to the minus 1 decay. Whereas coefficients where you have contracted twice with tangential derivatives, so one with L and another one t with t being any of the tangential directions, then you have that these coefficients behave better because of the null, because of the wave condition. And in fact, you see that derivatives of these metric coefficients essentially behave as tangential derivatives up to quadratic corrections. So they have a better decay, t to the minus 3/2 plus. Okay, and so using these arguments, you get around these weak null terms. And then it remains to estimate commutator terms. These are, of course, obtained when, so you want to propagate the energy estimates for your solution that carries a certain number of vector fields. So you apply these vector fields to the equation, you get the commutator terms, which I have highlighted here in red. And of course, you distribute these vector fields among the different factors. So I did not write all of them. And I just want to focus on this first one where all the vector fields fall on H, okay? And then the issue, and so what you would like to do, since this one carries a high number of vector fields, essentially what you want to do is to estimate these terms in L2 by estimating this term here in L infinity and this one in L2, right? Okay, the usual stuff. But then you recall that this term here decomposes into two parts, a massless wave and a massive wave. So the massless part is not well controlled in L2, right? Because the energy controls the H1 is at the H1 level of the solution. So these terms here that doesn't have a derivative is not well controlled. All right, but then when you have, okay, and then you also have to remember that this other term here is made of a massless part, a wave part, and a Klein-Gordon part, essentially. So when you have wave-wave commutators, this is essentially goes in the same way as in the work of Lindblad and Roniansky, for instance, in the sense that, all right, you express the metric with respect to the null frame. And in particular, okay, in this setting, since we are dealing with hyperboloids, we then express the derivatives with respect to the derivatives, the dt derivative and the derivative tangential to the hyperboloid. And then here, you use the fact that two derivatives of the wave gain extra decay with respect to the light cone, right, in R minus T. So you can use this extra decay to perform a Hardy type inequality alla Lindblad and Roniansky, where you can exploit this decay to essentially bound the L2 norm of this term by the energy. So you get away with it by using that type of argument. The issue is that you also have wave Klein-Gordon commutators, right? Oh, I'm sorry. Wave Klein-Gordon commutators, where here you have the massive part. And Klein-Gordon solutions do not gain any extra decay when you put extra derivatives on them. And so even second order derivatives of these metric coefficients will not decay faster than t to the minus 3/2. And so they decay to the t to the minus 3/2. And if you want to perform a Hardy inequality here, now you recall that in order to do a Hardy inequality, you have to trade a R to the minus 1 factor. So you start with a decay t to the minus 3/2. You trade a minus 1 decay. So what's only left is s to the minus 1/2. Okay. So this is responsible, then you do Gromwall, and this is responsible for the s to the 1/2 growth of the energy for the entire solution. Okay. And one remark is that because we compactified on S1, this term, this mixed term, is absent in the equation for the massless part. So we can propagate for those better energy bounds than the one for the full solution. And we really take advantage of this, okay, in our hierarchy. And to conclude the talk, just a word about the propagation of the pointwise bounds. So the pointwise bounds, the sharp pointwise bounds, and then derived directly from the equations, they satisfy our functions satisfy. So for the massive part here, we just look at the equation and it satisfies, and we get decay by rewriting the equation in hyperbolic coordinates using an approach that was already developed by Kleinerman for Klein-Gordon equations. And the thing that we should have to pay attention to is this red term, which is a quasi-linear term that cannot be absorbed in the left-hand side. And it is really proper to our Kaluza-Klein setting, and that, for instance, is absent in Einstein-Klein-Gordon, where the coupling is a weaker coupling between the scalar field and the metric. And is exactly this term that also requires, okay, the hierarchy between the energies and the pointwise bounds with all the parameters that I have introduced, and in particular that zeta was much smaller than gamma. And also important here that the pure wave-wave interactions are absent to get the, say, s to the t to the minus 3/2 decay for this Klein-Gordon part. And finally, for the wave component, we also go and look at the, we derive the the sharp pointwise bound from the equation following results that were already out there by Alinak, Asakura, and Katayama Yokoyama. And then by getting suitable pointwise estimates of the nonlinear terms. And this allows us to run the bootstrap arguments and to prove the result. Okay. All right, so that was all. Thank you for your attention.